So Hooke's law is something we need to understand before we can move on to looking at elastic potential energy, the energy that's stored in a spring. And this is a really important idea because ultimately we can model the forces and interactions between atoms as being spring-like and look at stored elastic potential energy in molecules too. But the basic idea is if we have a spring that has a certain rest length or relaxed length, so that it's normally this long here, and we can then define the origin of our coordinate system as being right at the end of the relaxed string. So this is x equals 0. If we pull the string, we have to apply a force to do that. And the reason we have to do that is that the spring itself is pulling back. So we've got Fp here as a pulling force that pulls to stretch the spring, and the spring is pulling back against that, resisting being stretched. And you'll notice that the force of the spring is in the opposite direction to the displacement, the change in length of the string. Similarly, if we compress a spring, we have to apply a force to the left here, Fp, to squash it, and the spring pushes back against us, and again that's in the opposite direction to the displacement of the spring. And for a lot of springs, not for the full range of motions you can get, but for a certain range of either extension or compression of a spring, it'll obey Hooke's law, which basically tells us that the force exerted by the spring is equal to minus, and the minus sign signifies that the force exerted by the spring is in the opposite direction to the displacement, a constant k multiplied by that displacement of the spring. Sometimes you'll see this written as minus k times delta x, where delta x represents the change in length of the spring from its original relaxed length. But the force exerted by the spring is minus k times delta x. So the force is proportional to the displacement. The more you squash the spring, the harder you have to push because the harder the spring pushes back. Or the more you stretch the spring, the harder the spring pulls back and the harder you have to pull. So this isn't uniformly easy. The longer the spring gets, the harder you're having to pull. Force is proportional to delta x. So on the next slide, if we have a graph of F versus delta x, it looks like this. Here we've got plotted, rather than the spring force, we've got the pulling force, the external force that's being applied, and that's going to be equal to k times x, which gives us a linear relationship between force and x. And we get round to and if you extend the spring by a distance xf, then looking at this graph you can see that the pulling force is not the same. It's small over here, it's big over here, but over the complete range of movement from 0 to this xf, the final extension of the spring, the average force, the bar over the top signifies average, so F bar is F average, is 1/2 of the maximum pulling force. So if you've got a spring and you've stretched it to a length x sub f, the final length, at that point you're pulling with a certain pulling force. The average force that had to be applied in order to stretch it that distance is 1/2 the pulling force you're applying at the end. And so that's 1/2 times k of fx, kx, because you remember the pulling force is equal to kx as written here. Okay. Now what we can do is consider what's the work done by that pulling force. Well, it's that average force multiplied by the displacement, which is 1/2 k times xf squared. So this is the work. You grab hold of a spring and you pull it. This is the work that you've done on the spring in order to stretch it. Now, according to the work energy theorem, If nothing else was going on, that work would have resulted in a change in kinetic energy of the spring. But that's not what's happened because something else was going on. The pulling force of the spring was in the opposite direction, so the spring itself did a negative work. Just like the pull of gravity does negative work when you try to lift something up and stores it as potential energy in the gravitational field. So the spring itself pulling back on you does negative work and stores that energy up. Stores up the energy that you put in as potential energy. So this is U sub S, spring potential energy, and it's equal to 1/2 times K times the extension of the spring, the change in length of the spring. And this number K, the spring constant that turns up in this calculation of energy and also in this calculation of how big the force has to be, that's unique to a particular spring. It's a function of the spring itself. So we've got those two important concepts, that you can store energy as potential energy, which you can then use later. If you've got energy stored in a spring, if you release the spring, it snaps back to its original length and can start something moving. If you've lifted something up, you let it go, it falls back down again, gains kinetic energy. So they're both ways of storing energy, either in the gravitational field or within the spring when it's being stretched.